Hey guys, here we'll be talking about simply supported beams with central point load. The central point load using double integration method. So this is a simply supported beam having a central point at the midpoint, then deflecting, that's sagging, and having its maximum deflection at y. Then we have the angle of the slope as IA, or you can write theta. So these are the reaction at A and B so this is a distance x from point B. So the total length is L, then L over 2. So the reaction at A is equals to the reaction at B, that's W over 2. Then the maximum bending moment equals to RB times X, RB, or you can put RA. So that's W over 2 times X. So the positive sign there indicates that it is sign of sagging. So then we proceed. So mx equals from what we derived from formula for maximum bending moment is flexural rigidity EI times the deflection, the square y over the x square. So we proceed using our integration method from our knowledge of further mathematics or mathematics. We have this formula for integration, then we input it and apply it to integrate this. So we input mx, which is wx over 2, that's the weight times the distance over 2. We derive it from here. Mx equals this. So come back here, then we integrate. So when you integrate, we resolve it to be this. So the coefficient 1 over 2, you bring it out, wx. Then when you integrate it, this having a power of 1, it becomes raised to power 2 when you're using this formula. So then you proceed and get equation 2. After getting equation 2, when x is L over 2, when x, I told you here that x is at a distance from, we assume that x is at a distance from B. We just assume. So let's say x is from here to the midpoint, that's x equals L over 2. So when x is equal to L over 2, then dy dx is 0. So you just substitute it into the equation 2, then we resolve it to be this. I've shown the step, so follow it gradually. Then we get the value of our constant for the boundary condition is obtained. So we substitute the value of the constant into equation 2. We put C into equation 2, into this equation. So we resolve it to be what? This wx square over 4 minus wl raised to power 2 over 16, then equals to bending moment. So this form equation, the EI dy dx, as equation 3. Then this equation is the equation of the slope at any section. It's the equation of the slope. So in this place we are going to be replacing this dy over dx equals to theta. Theta you can represent as theta or I, representing the slope. So maximum slope occurs at A and B, at both A and B. So the value for the slope at A is the same as value at B. That's what it means. So thus for maximum slope at B, we substitute x. So we chose one of the slope at x equals 0. So what will be the slope? When you put x equals 0 into equation 3, what do you get? You will get this. Then get our formula for the slope as this. So the negative sign there is showing that is a downward deflection, that the slope is a downward deflection. So when we resolve, then we go to the second integration. Don't forget we are doing double integration, then you integrate it the second time. It's the same step, just follow it. You write the equation 3 where we stopped, equation 3 where we stopped, then you rewrite it, then you integrate. When you integrate, you derive this, then you get another condition constant for the condition of the boundary. So when you integrate, ei dy dx becomes this. Then when you integrate this, you get this. So everything is already simplified, just follow the steps. So we get equation 4. So after getting our equation, we say when x equals 0, when x equals 0, then y equals 0. When x is 0, y is 0. So that will be what? To get the value of the second constant of the integration for the condition of the boundary. So when you substitute it into equation 4, we resolve it to be this, So C2 is equal to 0. So if you bracket it or put in a box showing that equation 5. So this equation is the equation for the deflection at any section. So we have got it for equation for the slope. We have got it for slope. So this is for deflection at any section. So note, maximum deflection occurs at the midpoint C from the diagram. So when maximum deflection occurs at point C, so x will be what? The same thing as L over 2. So we substitute L over 2 into the equation, then we get this. So when you substitute it, follow the steps that will be broken down for better understanding. So we resolve it to be this. So we get the equation for maximum deflection. So this is the equation, this is the final equation. So the negative sign there is indicating that is what? Downward deflection.